afternoon, everyone. My name is George Ntourmas, and I'm going to present to you my work on detail sizing optimization of laminated structures. As you have all probably understood by now, I'm one of the 5 OptiMACS ESRs, early stage researchers, and my work mainly has to do with second sequence optimization. But let's take a closer look into what exactly this optimization entails. So what we want to do is define our design variables in our problem. We want to define the optimum number of plies, the optimum orientation of each ply within the laminate or the structure. And since we're talking about large-scale aerospace structures, which are expected to be to have a variable stiffness, we also expect thickness changes across the laminate, and therefore we expect to have ply additions and ply drops. So in addition to all the rest, we need to find out which plies should be dropped and where exactly these plies should be dropped. As for the objective function of the problem, for this presentation, it's something as simple as a weight minimization of the structure, but we can also have other objectives such as a performance maximization of the aircraft, for example. Now, when it comes to constraints, they are split in 2 categories. I'm going to first start with the physical constraints. These are the classic constraints structural you would expect, such as strength, buckling, eigenmodes for the structure, for example, and then
George,
yeah.
Please, this is the we don't see the slides. Probably you're just sharing the. You're not sharing the right screen, I guess.
Okay. Or maybe you were in presentation mode.
Yeah, I went in presentation mode. Maybe that's. Okay, give me a second. Apologize about that. You can't see the screen now, right?
Yes, I can see the screen.
Okay, and if I go into presentation mode, you cannot see it?
We can still see it, but are you at the third slide? Or?
No, this is the first slide. What exactly can you see?
We see the PowerPoint in the normal mode. So if you go to presentation mode, we don't see the slides changing.
Oh, okay. It's the first time I had that.
I think you need to share the presentation mode.
Yeah, yeah. What about now? Can you now see it in full screen?
No.
Wow. Well, when I go into full screen mode.
Georgios, when you share it, you should share the desktop. Have you done that? If you share a screen, sometimes
I see it. Oh no.
Okay.
Yes, now.
Yeah, okay. Well, I sincerely apologize about that. Well, the thing is, you haven't really missed something very important. So I was talking about. It's fine right now, okay? Is it okay? Yeah, I guess so. Okay, so I was talking about the design variables of our problem, and we have physical constraints such as strength, buckling, eigenmodes, but the constraints which are of more importance for our problem are composite rules, and these are further divided into 2 subcategories. First of all, well, to begin with, these composite rules stem from engineering practice, we usually want to minimize some coupling effects or minimize some stress concentrations. And firstly, we have design rules which regulate what exactly happens within a specific laminate. So we usually use symmetric laminates in the aerospace industry, or we have other rules specifying that we shouldn't have more than 4 plies of the same orientation placed consecutively within the laminate. And then there's manufacturing rules, which, as I said, we're going to have a structure which varies in thickness across its span, and between neighboring zones or patches, as we usually call them, manufacturing rules regulate how these transitions exactly happen. And most important of them all is continuity constraint, which basically between 2 patches which are neighboring, it says that the plies within the thinnest one must be a subset of the plies in the neighboring thickest one. But what about the optimization algorithm that we choose to solve this problem? We can differentiate between 2 big categories here. On the one hand, we have gradient-based algorithms which work very well with the size of our problem and with the physical constraints which need to be evaluated with the finite element model evaluations, which are quite expensive. But these algorithms work better with continuous design variables, and our problem, especially the part with the composite rules, is a very discrete problem. And for that reason, gradient-free algorithms might offer a better, but they come with the drawback that we need many evaluations, and then the computational cost becomes prohibitive. So a compromise, what we have chosen to do, and what also other researchers have done to deal with optimizing such large-scale structures, is split the optimization process into 2 distinct stages. The first one, which I here mention as a continuous optimization, is a gradient-based optimization, and we parameterize the structure using the concept of generic stacks, to which I will mention in the next slide, while other people have usually used other parameterizations such as lamination or polar parameters. The result of this is a continuous thickness and stiffness distribution of the structure. We then need to perform a simple discretization of the thickness to get an actual integer number of plies that we can lay down on the structure. And then comes the second stage of the optimization, which is the discrete. And in this stage, what we want to do is we keep the thickness fixed, and we want to match as closely as possible the optimal stiffness coming from the first step of the optimization. And we have formulated this problem in a slightly different way. I'm going to talk about what exactly we do in a next slide. What I want to emphasize here is that after the first step, we can be sure that the physical constraints, so buckling constraints, for example, in our problem are satisfied. But what we know is not satisfied are the composite rules. And this is because composite rules are discrete, and we have a continuous solution over here. So that's when the second stage comes into play. And after the second stage, we know that the composite rules are going to be satisfied. The question is what happens with the physical constraints. And to know that, we need to go back and reevaluate the structure once more. And then there's 2 possibilities. If the physical constraints are satisfied, then our job size in the structure is done. If not, we need to go back, increase the design factor, and perform this 2-stage optimization loop again until we converge into all constraints in the problem being satisfied, basically. So starting now with the first stage of the optimization, this is performed in the framework of an Airbus multidisciplinary optimization platform, which is called Lagrange. And I mentioned before that we use the concept of generic stacks to parameterize the structure. This is actually very simple. A generic stack is comprised of many generic layers whose stacking and orientation is fixed and remains fixed throughout the optimization. And what is allowed to change is the individual thickness of each one of these layers during the optimization. And by varying these thicknesses, we can achieve both a thickness and a stiffness optimization of the structure. Of course, all of the physical constraints are taken into account in the gradient-based optimization, and before I joined, there were already some of the easier, let's say, composite rules like symmetry and balance, which can be easily enforced. During my work, there has been an attempt to introduce as many of these composite constraints as possible in the first step, because it's very important. We're going to see that in the next slides. It's very important to have as many as possible in the first step, and most important of them all is continuity constraint. Now, as for the second stage of the optimization, I said that we perform an intermediate step here in between where we discretize the thickness. So the thickness is fixed throughout this optimization. The weight of the structure is fixed. And what we're trying to do is minimize the absolute difference between the stiffness of the continuous and the stiffness of the discrete result. And we have come up with two different formulations of these problems. They basically do the same thing, but they have advantages and disadvantages. They mainly differ into how continuity between neighboring patches is treated, but I won't go into any detail in that. The thing is that to get this kind of formulation of the problem, we can use any kind of design variable we want, whether that is continuous, integer, binary, whatever, but we need to make sure that the objective function and all of the constraints are formulated as linear functions with respect to our design variables. And once we have concluded to this set of equations, we basically feed a lot of these equations, all of these equations actually, inside a commercial optimization software that is able to handle such problem formulations. I'm now gonna start with showing some results, and we first see here some results coming out of the continuous optimization, the first stage, some continuous results. We have a plate here consisting of 8 patches, which is rather arbitrarily loaded, and here we see the ply share distribution between the different patches if none of the constraints if no constraints are applied in the first stage of the optimization. And we can see that it's quite inhomogeneous, and there's no way continuity is satisfied for these two neighboring patches or these two neighboring patches, for example. Things change when we apply the continuity constraint. We can see that the result is a much more homogenized result in terms of stiffness. And it's also something that we couldn't really have anticipated. If you examine, for example, the thicknesses between these two patches, the optimizer has jumped to a completely different optimum when activating this constraint. Of course, we have other constraints as well, but they're not as influential and important as this one. For example, if maximum grouping constraint, which specifies that we shouldn't have more than 4 consecutive plies, let's say, of plies of the same orientation placed together. If this one is activated, here areas where we had the high concentration of 0-degree plies are further broken down into smaller regions. Before I go on, I want to emphasize the fact that no matter what input we provide to the discrete optimization, whether this is a rather good input, so something homogenized coming out from a first stage optimization with the continuity constraint activated, or whether this is a rather bad input, like the one we saw without any constraints, the discrete optimization is going to be able to find a feasible solution that satisfies all of the composite rules. But the thing is, what happens with the physical constraints, and we can expect that in this case we have sacrificed a lot, so we're not able basically to match the stiffnesses, and we can see the effects of that in this slide, where in the first columns we basically perform the first stage of the optimization. We perform the first stage of the optimization without having the continuity constraint, and we're looking basically only at buckling in this simple problem. And we can see by the reserve factor here that we have a violation. A reserve factor is basically the ratio between the allowable over the applicable load. So everything below 1 actually indicates a violation. Things change when we have the optimization, the first stage of the optimization constraint. We can directly, after performing the discrete optimization, we directly arrive into something that fulfills all of the buckling constraints. The importance of having the constraints is highlighted by looking at what we would have to do if we didn't have the constraints, which is following basically the workflow, the unconstrained workflow. So we would have to go back and increase the design factor, as I mentioned. This is exactly what we do here. We increase the design factor from 1 to 1.3 to 1.6 until we finally arrive into something that fulfills the buckling constraint. In the meantime, we have significantly penalize the structure in terms of weight, and this is due to over-dimensioning, severely over-dimensioning some specific patches in the structure. Finally, I also have a different benchmark here. It's a benchmark used widely in literature. It's this 18 panels formed in a kind of horseshoe arrangement, and I'm comparing our work with a similar two-stage process by some other researchers, by McQuart. They have used a different parameterization in the first stage of the optimization. So they have used the lamination parameters instead of generic stacks, but they have actually formulated the continuity constraint within the lamination parameter space. The problem is that because of the particularities of this design space, which might have some advantages, but it has some particularities, and you can't really formulate this kind of constraints accurately within such a design space. And this leads to when optimizing with the constraint, when you perform a discretization of the structure, you see that you violate the constraints, and therefore you need to increase your design factor in order to get better. And well, they in their study, they didn't go all the way up to a reserve factor of 1. They would still need to perform another step here. But once again, for our work, we are able to, in one pass of this two-stage optimization, we are directly able to fulfill all of the physical constraints, which again, for this case, is only buckling for this benchmark problem. The effect I talked about can also be seen here, where we plot our results, which can be seen with the blue points, and the results from the other researchers with the red points. We plot them in a, let's say that this is our stiffness design space, or part of our stiffness design space, and we can see the difference between the continuous and the discrete results for the other work, which is quite a big difference. And this big difference is exactly what enables us to this big difference is the problem, because it means that you have to perform the optimization again, and you end up having a larger mass penalizing the structural weight, as we can see here. So to sum everything up, there has been a significant improvement on the past way of working, at least within Airbus, and we have seen lower structural weights for an academic benchmark, which I just showed. And finally, it's the first two-step optimization process, where we can actually get a satisfaction of all the physical constraints in the end, without having to go back, increase the design factor, and penalize the mass of the structure. As for the future, we're currently setting up an optimization problem to apply this process on an actual aircraft, on a large-scale structure, and see whether the results replicate as good as with the other benchmarks. And we're also in the process of introducing a second objective in the problem, formulating manufacturing cost as an objective. We're first going to start with a continuous optimization, and we expect to see such a behavior, basically, where as the manufacturing cost and the manufacturing complexity increases, the structural weight also decreases further. That was the end of my presentation. Thank you for your attention, and I would be glad to answer any questions you might have.
Okay, thank you also, Georg.